So, we will look into now interpretation of test results, right, interpretation of test results. So, we have already seen that condition survey has this kind of a flow diagram, remember, and I come to a conclusion and I suggest what should be done. But in the process, therefore, it is important that I look into interpretation of results, test result interpretation and all that. So, this is there. So, we will discuss this right now. It depends upon objective. First, it depends upon objective. Now, sometime, as I said, there is a little bit of doubt about the quality of concrete, nothing else. Strength is not soundness, you want to find out whether concrete is sufficiently sound or not. So, you can do a histogram plot of any one of the measured values. For example, rebound number index or ultrasonic pulse velocity, or if you have taken core, too many number of core or some strength index like capo or something like that, you can actually plot histogram to judge whether the concrete is uniform or not. So, uniform concrete will show a particular type of variation pattern, we will see that it should show normal distribution. Degree of variability is obtained through standard deviation. If I have high standard deviation, that means something wrong with my quality, and coefficient of variation I can find out because standard deviation divided by mean, and I can find out through this. So, if you want strength, then you have to do little bit of code testing by some means, either the cube or code testing. If you have the cube, because it is not a very old, not an old structure, you might use the currently available cube, correlate it to the indirect indices and then obtain the strength. So, basically in case of no cubes available, the code test and some in some indirect index and direct in situ strength, this you can put together and obtain a correlation and use this correlation to predict the strength later on. And simply if it is deterioration oriented, for example, like this somebody, there is a corrosion somewhere, say rebar corrosion has been seen, like I showed somewhere, not very serious actually, but you have seen some patches. Now, then there is no need really, not there is any need really to look into code test and things like that, unless somebody also wants to know, no, since this has happened, the core possibly the strength is also bad. Even if your strength is okay, still also rebar corrosion distress can occur, because that is related to the chemical thing, right, that is related to the chemical thing, because it might be contaminated with chloride from right from the beginning, and moisture is available, right, from various sources. Let us say maybe your pipe is leaking continuously subjected to moist conditions of the surface, no concrete can be zero porosity. So, moisture will penetrate into the cover concrete, it might corrode, although structurally it is still safe, satisfying the grade of concrete required for structural design. So, in that case, why do code test, or you do not need the core result, right. So, if you first of all you must know what is it, and diagnosing the cause you have to is also a part of interpretation of the results. So, uniformity of the concrete can be judged through histogram plot. For example, supposing it is a velocity, ultrasonic pulse velocity, quality is judged through IS 1331 or any other literature will give you. First thing you do is, it says that if the velocity is more than 4.5, the concrete is excellent. So, soundness of concrete you can judge through this. It is between 3.5 to 4.5, it is good, and it is 3.0 to 3.5, it is medium, below 3 it is doubtful. In such case, you got to do some other test to find out the core, because in that case you must do some other test like code test to find out the actual strength of concrete. So, if you are just in doubt, you need not find out the strength. Even if you see some sort of chemical distress and you think that okay, let us check, you do this test and that is over, you do not damage the concrete further. So, that is it, and this is the interpretation that is done. So, first if you find that okay, everything is here, I am not going to ask for further strength testing, I am not going to ask for further strength testing unless somebody insists. Now, we have seen that strength variation would be something like this, if I do large number of tests. For example, in this particular case, compressive strength varies from 42 to 67, and there are large number of data here. It is a population practically, and since the concrete strength is function of too many factors, many uniform distribution might make it normal distribution. That is what we have discussed earlier. So, concrete strength is expected to be normally distributed. Similarly, rebound hammer index is also expected to be normally distributed if it is same population. So, if it is same population, then you will get a histogram plot like this with single peak. If the concrete has come from same source, it is uniform concrete, you will get one peak, right. So, uniformity can be judged looking at the variation with any index. It can be rebound number, it can be ultrasound, it can be strength. So, soundness of concrete by ultrasound straight and uniformity of concrete by any of this. So, now you need not do code test to do this, strength is not necessary to be done. So, variation is normally distributed population. So, any index in concrete is likely to be normally distributed unless there is a reason for not. If it is random occurring everywhere, then it is likely to be this manner. So, average of course and standard deviation you know. Now, standard deviation gives me an indication of the quality of concrete, larger standard deviation means poor quality of concrete. So, this is let us say typically from a site, this is a bad site, as you can see the strength varies from 2 to about 22.5, large number of tests, but this is a predicted strength predicted from correlation between rebound number and code test, right. So, you can see, but the concrete is uniform, it is bad concrete. The average strength is somewhere around 13 or so, if you see, mean would be 13 or so, this is around 13 in situ strength, not equivalent cube strength, maximum is 22.6, it is in an actual structure building. Now, this strength is not very good, but it is uniform, that means it has come from the same source, contractor was one, material sources are similar, within reasonable variation. They are not different, two different contractors did not bring it, neither they were done at two different times and so on. So, this is uniform concrete, right. So, when number of data points are large, more close approximation of normal distribution is obtained. If you have small data something like 15, 16, you will get some sort of one peak variation, right. But if you have large number of data as it is here, because you can see the maximum is somewhere around 60, 70 or so, maximum the peak, its peak is somewhere around 70, 60, close to 70. So, large number of data predicted strengths were there in the whole building. It is a 14-story building, specific building, and this one can see that concrete was uniform. It was not very good concrete, might need strengthening, might have, but supposing you have some small lesser number of data, sometime you get this sort of a thing. Now, here actually we know that this particular cases two set of data, they are skewed on the left hand side. That means, this some concrete might have come later on, and we knew in this particular case they were constructed, some columns were constructed later and added later. In fact, since below balcony, because they saw some distresses, I added 2-3 columns, right, and we tested them, they were not again of very good quality, something like that. So, even skewed one would show that whether some, or some bad concrete is there or not. This is two distinct peak, which means that it would have come from two sources. Two distinct peaks means it would have come from two sources. Possibly two contractors would have supplied from two different sources of concrete, or maybe it was constructed at two different times. So, uniform single peak tells us that it is an uniform concrete, it does not talk anything of the strength has to be estimated. So, this is from two different sources, right, and this is all haphazard non-uniform concrete, one distinct peak, no distinct peak actually. So, in fact, it is no uniform concrete. So, actually it is all bad concrete, no uniform concrete is a bad concrete. So, you can actually from such histogram plot you can judge for any index you take, large number of data if it is available is better, you can judge whether it is uniform concrete or two suppliers were there, 2 times it was there, 2 distinct concrete or totally non-uniform concrete. So, this is the next interpretation, non-uniform concrete. So, this is the next interpretation. If you are looking at quality, then obviously you can find out the standard deviation is one thing, and large standard deviation obviously for each one peak, if you can separate out in this particular case, then for each one what was the quality that you can identify. It is single peak, then you can find out the standard deviation or CV. And remember, we had a CV versus strength graph earlier when we were selecting number of locations. We can use that to find out. There was one was in situ concrete, good quality, bad quality, 3 qualities were there. So, where your quality lies you can actually find out, right. For example, it was something like this, if you remember, this was strength versus CV. For very good quality concrete, in situ and cube, standard cube, it was somewhere there, bad concrete was somewhere up there. I showed you a graph earlier. So, you can make use of such available information to identify your concrete quality. Now, this is a particular case of large number of ultrasonic pulse velocity measurement being done. It was actually, as you can say, 17th floor building. Up to 324 locations were tested up to 6th floor, because the concrete were distinct. You can find out there are 3 different concretes and 5 medium, 6 doubtful locations. So, out of 324, in this case there is a different concrete. 454 tests were done on ultrasonic pulse velocity, 26 locations were doubtful. So, this set of concrete was relatively bad. You can see histogram plot we did same, they are normally distributed. So, we could separate out the concrete, and when you separate out the concrete, of course, total 42 were bad, but most of them were 7 to 13 floor. In fact, we found out that a bad different cement was used or something of that kind. So, you can actually do a lot of play around with the statistics when you are planning to do this kind of test. So, you can see that this zone, you can calculate out excellent concrete was maximum here. It was not many, but good locations were also pretty large. Out of 324, 285 were good. So, lower level it was better. It was 221 out of 315. So, not all that bad, but this set got 100 medium, 26. So, relatively this was much worse concrete. So, this kind of interpretation you can make, right, from NDT results. You can use rebound number also for similar kind of results. So, for example, you can like the tunnel lining I was showing, there this kind of results were available. Range of rebound number was some for A type of, remember that A I talked about that time when I was talking about 32 to 37. So, this data can be used for various cases for interpretation. We did use them earlier. The mixes were also known to us. In ABCD were some cases. A case, range of rebound number was 32 to 37, ultrasonic pulse velocity was 3.03, in situ cube strength was better, and we also knew the mix. So, these informations. So, some information, this from this kind of index, histogram plot, information about uniformity and quality of concrete, and where bad, which one is better, that sort of conclusions you can draw. So, standard deviation, for example, if you have this standard deviation, if you know standard deviation is this, then up to 6th floor mean number of sample, okay, etc. I mean basically mean was 4.1, the ultrasonic pulse velocity, mode was 4.7, median was 4.1, that means all normally distributed. So, from mean, median, mode calculations also you can find out. Standard deviation was 0.375, population standard deviation. In this case it was 0.357, right. So, this is for the next range, that was, and you can determine how many number of, in frequency diagram, how many number of class interval you should have using this formula. 3.3 log n plus 1, that is the number of class interval. If n is your data, for example, if it is 324, number of class intervals will be equals to 3.3 log 324 plus 1. So, that many number of class intervals. So, total data you divide into that many number of class interval and plot the histogram plot, right, plot the histogram plot and also find out standard deviation, etc. So, you see this same up to 6th floor, this was the kind, it was uniform concrete, right, but there are some bad concrete down there. So, it is skewed, there was some concrete bad, but not many bad. 7 to 34 it was still increasing on this side, right, ultrasonic pulse velocity result same one. I am plotting histogram and this histogram did not match with each other. Initially when we plotted we found different peaks. When we separated out we started getting individual peaks, and then 7th code test results, of course 7 to 13 showed some sort of thing. So, there is a skewness on the strength, 7 to 13 was the worst. So, we did not do code test there much. Here we did a number of them and we found that there are many of them having bad strength, because it is, you know, the good strength is less, bad strength is much higher. So, this kind of actually it is a distribution would be something like this, partially, you know, this is not feasible because below 0 is not feasible. So, partially distributed around. So, you know, so this is what it is. So, skewed result, physically impossible. Then we plotted with log of strength, then it brought it to log of strength, of course, and it showed that again 2 peaks from 7 to 13th floor, the same building. 7 to 13th floor had bad concretes that we have seen. We started going examining it more, and now after a log strength plot we could find out some concrete is bad, somewhere something went wrong, rest of the concrete is perhaps okay, 2 different distinct peaks we found out. So, analysis of interpretation can involve, I am giving you examples and the basic theory, you can apply those statistical concepts, not very complex, very simple, take the total data, divide it into n if the number of data, let us say the number of class interval Ci, let us say n Ci will be equals to 3.3 log n plus 1. So, 1 2 here 7 number of class interval, because 324 whatever the value was 454, log of 454 will be how much, something like 2 point something, 2.6 or 2.7 or something. So, you calculate out that and you will find that we can actually, you know, it would come something of that kind, or maybe less than 324 or something. I do not remember how much 7 to 13 data were there. How much does it come? So, number of intervals can be determined in this manner, and then if you find 2 such peaks, obviously it is core strength, yeah, core strength was not 454, it was less. So, even 454 if it was, how much it is, how many number of class interval I should have, how many number of class interval I should have, 10 I should have 10. So, that is what we do, you know. So, we do 10 class interval. For core it was number of cores were less, and when we do log we get 2 peaks, log strength we plotted now, and we find 2 peaks, because normal strength plot was not giving me a good one, because skewed to the standard deviation minus 8.72, which is infeasible. We thought why not relate to the log normal distribution. So, you know, so this is what we did and it works sometimes, that is what I am saying, and you know the FCK is 95 percentile. So, great strength one can obtain using some of those. So, one thing you must know, that design strength used in design is basically first to take care of the actual structure condition and standard cube difference, because of the adverse loading effect, and also production is not same as the cube. Cube is produced in a standard manner, cured in a standard manner, and tested under uniaxial compressive strength in a standard manner under given type of load. While in actual structure things would be different, and that is why you multiply this. Actually, it is 80% of the 85% of cylinder strength, right. So, 0.85 and then cube strength if you are doing. So, this is, I think I might have explained sometime, it is 0.67 FCK. Then partial factor of safety over this is 0.67 FCK divided by 1.5 FCK. So, actually strength you use in design is this, right. So, one of the thing it says is that you find out the FCK value, in situ FCK value. An earlier code, British code would say that your actual measured FCK, in situ FCK should be multiplied, it should have a factor of safety of at least 1.2. So, if you are in situ 0.67 divided by 1.5 FCK multiplied by 1.2, because this is what you have used in design, multiplied by 1.2, which is a factor of safety, your strength should be at least more than that. Indian code of course adopted that this should be at least, mean should be 85%. I will just look at that interpretation right now. So, design strength is lower, that is what we know. Strength used in design is lower, then there is a partial factor of safety. So, use 0.67 FCK, right. And this is what British code was doing earlier, one of the British codes. Strength estimation strategy, a minimum factor of safety of 1.2 was recommended. Therefore, that they said that you determine from the worst location in the site FCK and in situ FCK, and that should not be more than 0.8 FCK value. Determine the strength, in situ strength, average in situ strength in worst location in the site, which is most doubtful, and it should not be less than 0.8 FCK. That is the British code, earlier British code says, right. But Indian code of course does it in a different manner. Mean strength should not be, if you measure in the site, mean strength should not be, in situ strength should not be more than 0.85 FCK. And I have told you how to find out mean in situ strength through cube strength. So, and core strength, core strength. So, core rebound hammer correlation, core capo correlation, core USPB correlation, anything you use, you are able to find out in situ strength. That in situ, mean in situ strength should not be less than 0.85 FCK, and the least value should not be less than 0.75 FCK, least value, lowest value in situ strength, because in situ strength average should not be more than less than a 0.85 FCK, and this is actually again kind of a guideline. EN 65, EN now European code, which is also British code as part of European code, 1379 says FCK IS, first you determine FCK in situ, and this should not be less than 0.85 FCK. So, you see the earlier British code was different, it says that you find out in worst location average in situ strength, that should not be less than 0.8 FCK. Indian code says you find out in situ strength, average in situ strength should not be less than 0.85 FCK, and minimum in situ strength should not be less than 0.75 FCK. And this EN code goes a little bit, it gives you a way to estimate the FCK in situ. How it does? It takes 3 cases. If you have 3 to 14 cores, you use approach B. I will tell you what is approach A, which is number of cores more than 15, then you use approach A, and indirectly through correlation is approach A, right. So, alternative there it gives you alternative 1 direct correlation with core, alternative 2 limited cores, and they gave a basic curve, and from there you establish your own correlation. So, something let us see what each one of them is. Actually that is very elaborate. So, it says that if you have more than 15 cores, find out the mean in situ strength. So, 16, 17 cores you have found out the mean in situ strength, then FCK in situ is given by FCK mean, F mean in situ strength minus 1.48 standard deviation. This is that Z value or equivalent T value or whatever it is, they have suggested this value, right. And FCK or FCK IS plus, FCK in situ will be taken as FCK lowest plus 4, whichever is lower. S should always be more than 2, it cannot be less than 2, it is not feasible. If it is less than 2, then also you got to take it as 2. So, you find out FCK IS. Now, this FCK IS should be greater than 0.85 FCK. So, if it is M30 concrete or M20 concrete, 0.85 FCK is 17.17, right, I mean 17 MPa. So, in situ strength mean strength minus 1.48 standard deviation should be more than 17. So, in situ strength, mean in situ should be minus 1.48 standard deviation, which is FCK IS. So, this value should be greater than 17, then it will be satisfying M20 grade of concrete, right. So, this you determine this number of, take from 16 cores, find out mean strength, that minus the standard deviation from those cores, then you get this. So, this has taken an average value for a given confidence level, right, or FCK lowest plus 4. So, it is also taking care of the lowest plus 4, whichever is lower. So, that is the EN code. If it is approach B is something like this, it says if it is, you can't have less than 3. So, if you have 3 to 14, then approach B where it says FCK same, but here it is not specified 1.48 s, but it says K. Now, K varies, K is the number of, K depends upon number of cores. Supposing it is 7 for 3 to 6 cores, 5 for 7 to 9 cores, and 5 for 10 to 14 cores. So, this K value now no 1.48 s, it is simply suggesting you values. Basically the same, how much is a, because if you test small number of samples, estimated standard deviation is not the true, it is different than the population standard deviation, because of sample size effect. So, you use what you call T distribution, S and sigma, S is for samples, sigma is for population. So, to take care of this kind of situations for small number of samples, it does not want you to get into too many statistics, but simply gives you some guideline based on, but the concept behind this is same, sample size statistics related to small samples, size of small sample size. So, it gives you this, and you can see that this is much more elaborate. In fact, if I have to use, and nobody insists that okay, you have to use Indian standard code, I use this 13791, which is much more elaborate, right. So, that is how interpretation of strength is done. So, this is what it is, and okay, that is what it is. Now, if it is other approach is there, other approach is there, then also it says you can establish the correlation, strength from correlation. In that case, it is this value gets changes, standard deviation should be greater than 3 at least, right, if you are using the other approach. One approach is direct core 3 to 14 or more than 14. The other approach is through correlation. Two approaches I talked, A and B. So, A is through correlation. In that case, it says that you establish your correlation, concrete specific correlation based on some basic curve it is given. So, basic curves are of something of this kind. X axis you will have some index, rebound number index, ultrasonic pulse velocity or strength, and this is the in situ strength or core strength or whatever you have found out, and it gives you a basic curve for each type of correlation that you are trying to establish. Yeah. So, each type of correlation you are trying to establish, and then you say you find out your deviation, it gives you a way to actually establish your own correlation. But I found it that it does not work in Indian condition, because your curve would be something like this, it does not match. Maybe they have arrived at it from the European conditions. In India, you have to establish your own correlation using all statistical regression, and there is no other way, using statistical regression no other way. So, the basic curves are available for rebound MR, ultrasonic pulse velocity, pull out test, etc. Several curves are given, and you can use them if you want to, but my own experience that in India perhaps it is better, do not use basic curves, you try to establish your own correlation. Basic curves simplifies the regression process, but today with so many statistical softwares available, one can develop their own curves, but you need large number of data in that case. So, basic curves are very much there. So, basic curve for rebound number test is like this, basic curve for ultrasonic test. So, deviation of your curve, your points from the basic curve you find out, and then it gives you a procedure to establish a new curve, which was the top curve, which is your curve, which is your curve. But if all your results are coming down below here, you can't actually use this thing. So, as a result there is a problem, we can't, I mean so far I was not able to use this basic curve for pull out test. So, BS code provides all this, right. Okay, so that is now you know this already I have told you. Now, this is a correlation that sometime you might get. For example, this is a correlation I am showing between rebound number and strength from actual site. So, this is what it is, but if you take log strength then it comes out to be better. So, may have to do a little bit of statistical jugglery depending upon the sometime log curves fit. So, you have to fit a best curve. This is a log curve fit much better. You know this was sorry, this was neither was fitting very well, but then something we did actually, we did something a multiple correlation. So, use see this was single, if I was using single rebound number index I was not getting good curve, but I had data available for both rebound number and ultrasonic pulse velocity data. So, then I use a multiple regression and I use log strength, and in that case I get actually relatively much better coefficient of determination. It is not very good, but still it was order of around 0.61 or something of this kind, I think, you know. So, the equation came out to be something of this kind, 0.16 rebound number plus 274 B 10 log strength. So, this kind of, you know, you can improve over your correlation if you use more than one variable. Multivariate regression, and we have done simple linear regression using Excel. So, statistics can be used. First you try to do your own correlation, otherwise you have to do too many cores. So, we restrict it, maybe take 20 cores in a large building, that was 6 to 13 story 17 story building. So, you could take a lot of cores, and but then we had to take only between 6 to 13 because we stratified now. 6 to up to 6 we found things were better, and above 13 was not so bad. Problem was with 6 to 13, which was a different concrete. So, we took 6 to 13 means 7 floors, large area, you can take 20-30 cores to establish your 30 cores, you know, large more number of tests, you can establish your correlation. But there also we are finding that correlation was not very good. Then we use rebound number and ultrasound together, and multiple linear regression we use using Excel. Linest is the function available in Excel. So, it is not a problem these days to do all this, and it gives us better, at least 80% of the, nearly 80% of the results were. So, this is the kind of curve, 0.62 it was coming R square, it has improved 0.09 it was showing earlier, no correlation actually. Now, it is 0.62, which means about under root of 0.62 is around 0.7576. 76% or 77% of the results are explained by this kind of correlation. So, that is it. So, you know, that is where it is. So, we used this mode data, then we said you do mode tests. Few more tests were done, few more cores were taken, and we did improve the situation even better. So, we got somewhat better, right. So, this was you know this is the kind of scenario you can actually improve it by doing, then you do more code test result, establish better correlation. So, finally, we did a better correlation, we established, and this line seems to be fitting better both the strength, and then we predicted strength in many places where we have only taken rebound number and ultrasound, which was 350 or something of that order. Cores were much less, where so we could now get full information about the strength and which column needed strengthening, which it did not need strengthening. We can segregate out. Actually, we saved on to the cost, because all columns, some columns we could say it was all problem of columns, nothing else. Some columns we could say that this, you know, earlier we would have done en masse, but we decided that only some columns will strengthen, some columns will not strengthen. So, this sort of things you can do. Okay. So, this is you know, some cases you may have to predict shrinkage, right, shrinkage stresses, and ACI 209 gives you how to estimate shrinkage. Shrinkage cracks, some cases we did use this. I think I will not go into details of estimation of shrinkage, but shrinkage can be estimated from ACI 209R, and the relation, if you have this data, and if calculate the shrinkage, we have seen, remember we talked about the tunnel lining, there are cracks, and we thought some of them were due to shrinkage cracks, early shrinkage or drying shrinkage cracks. Then we estimated the shrinkage using SCI 290R, and then we found out the ultimate shrinkage that is possible, and calculated them, and calculated value, then we correlated, and then what we did was, the strength development, how the strength will development. So, tensile strength will develop in this manner as a function of time. This was based on, again, E will change in this manner. Tensile strength formula is available for moist cure scenario. For other curing scenario, this is also available. How the strength will extend. This is a British code practice, BS 8110. It will give you how to find out the strength. Therefore, tensile strength, how it increases, that is known to us. We found out how the strains, shrinkage strains, therefore, multiplied by the elastic modulus, taking care of the positive creep effect, we also calculated creep, and we can predict when the tensile strength, the induced elastic stress will exceed the tensile strength. It was induced stress will exceed the tensile strength. The number of days, so T days we could find out, and T days when we tested, it was, say this T days comes out to be, let us say something like 60 days, and we did testing at 6 months or 1 year. So, therefore, we could actually say that diagnose this, it is actually shrinkage cracks. First visual observation, we identify from the nature of crack that is shrinkage cracks, we can do some calculations also. This is available in Neville and Brooks book, this is available in Neville and Brooks book or many other books. So, this is what we did, we plotted the tensile strength, average shrinkage in the wall with time based on this ACI formulae, and average strength development was given by tensile strength is at pink ones, this curve. Therefore, the age at which actually, this is not minus, this age at which actually cracks should have started, initiated, we could find out. So, average shrinkage stress and tensile strength of concrete with time. Therefore, since the stress exceeded the tensile strength, it would have cracked at this point of time, and we might have tested somewhere around 60, last test we did 2 months later, I mean whatever it is, 60 days, after 60 days. So, therefore, one can justify your diagnosis by theoretical calculation. Interpretation will include all this, it is just not purely something, simply you can, some notional thing one can write, a lot of science can, concrete science can go into it. Last case I will just discuss in 2 minutes, 2 to 3 minutes. This is a case where we had to compare. This is a case where the cement strength should have been 53 grade, cement should have been 53 grade. When they tested, they found it out to be 47 MPa. So, it did not satisfy 53 grade requirement. It was a pre-stressed concrete actual structure in Delhi, right. So, concrete cube test was also satisfactory, but there was a query from the investigation agency, financial investigation agency, like CBC and things like that. They said that it was 53 grade, you use 47 grade, but then you can't do the test, the structure is already, it's a it's a bridge structure, it was, or flyover structure, it was actually in operation. So, I can't take any core, or I can take limited, I can limited damage I can do. So, what we did capo test, very limited core test and lot of ultrasound test, and compare the results of those places where cement not satisfying 53 grade, that span where cement not satisfying 53 grade was used, and some other span where cement satisfying 53 grade were used. Compare the properties, and if the properties were same, and I have already said that that satisfactory, the one having correct cement is satisfactory, then this should be also satisfactory. So, we used a comparative evaluation. This can be done compliance to specification basically. So, implication is we just looked into investigation by comparison, and what we did, we actually set the ones. So, we called this the one satisfying requirement, we call it concrete B, one not satisfying requirement, we call it concrete A. Requirement of cement, not the concrete, because it is a requirement of cement. And then the grade of cement existing concrete cannot be conclusively identified. I can't do chemical testing and identify grade of cement. So, therefore, we went to the final product, and what we did lot of non-destructive testing. We said that concrete B is deemed to satisfy all the properties requirement, and we says in design including those required for adequate safety and structure, provided it is as good as concrete A and B are saying. That is what the point, and this statement says all, which the slides you have. So, to test hypothesis that surface hardness, soundness and solidity of concrete A is as good as B, we would compare them. So, what we did? We did USPB, capo, rebound hammer and limited core test to see that things are correlation is okay. The hypothesis testing we use, statistical hypothesis testing we use, that concrete A is as good as concrete B. So, basically statistical hypothesis testing we did, right. So, null hypothesis we established, mean rebound hammer standard deviation for concrete A was this, concrete B was this, USPB was this and capo was this. Then we use simply the hypothesis testing, right. So, capo correlated, so there are three types of statistical test is there. We looked at integral absolute error for all of them with this with the core. So, we found that this is reasonably good. Capos gives you reasonable understanding of the in situ strength, that is one thing. They use that integrated absolute error in order to find out whether capo and core matches or not. And then what you did, this is the Z value, null hypothesis that mu A plus mu B is equals to 0, and alternative is hypothesis mu A is greater than mu B, because one mean of one concrete is better the other. So, this hypothesis testing we did and calculated using statistical formula, and all these values are here actually, and we found out the critical Z alpha value for this case with the level of significance of alpha equals to 0.05, it was 1.645, and use statistical hypothesis testing, right. And we could conclude, I am not going into the statistics unless you are interested, you can look into this detail is available here, and we could establish that concrete A is as good as concrete B, by doing simple statistical testing for each type of test, first for the rebound number test, then for the ultrasonic test, and then for the capo test. So, final finding was something like this, So, this is what it is, and if it is corrosion distress test, then we do of course all this number of tests what I just mentioned earlier, half cell potential, and this is another case of, then you suggest remedial concrete, some remedial measures suggested based on this. So, I think with this I would like to conclude our discussion, right.